Let's get started. So we have Professor Shubhanshu Shekhar here. He is assistant professor who joined our department starting from this semester. Welcome. And this is, I believe, your second seminar here, right? The first seminar is your job talk. I was really impressed by your job talk, so I'm looking forward to this one as well. Yeah.
Thanks. So good afternoon, everyone. So today I'll be talking about my work on permutation-free kernel hypothesis tests. So this talk will be based mainly on these two papers, which I've written jointly with my co-authors, Ilmun Kim from Yonsei University and Aditya Ramdas from Carnegie Mellon. So here's the outline of today's talk. So I'll begin by presenting some background about the problem of two-sample testing. And then I will introduce a class of two-sample tests based on this notion of kernel maximum mean discrepancy metric. I'll describe some of the existing methods based on kernel-MMD and discuss what their problems are. And that will lead us to the second part of the talk, in which I will propose a new kernel two-sample test, which addresses those problems. And then I will describe how the same ideas can also be used for other problems like independence testing. And finally, I'll conclude with some of my ongoing work and some open questions. Okay, so let's begin with some background on this problem of two-sample testing. So to motivate this problem, let's look at an application of clinical trials. So here's a very simplified version of how clinical trials are conducted. So we begin with a pool of patients who are chosen so that they have some roughly equivalent characteristics, and they are randomly divided into two groups. One of the groups is assigned, let's say, a treatment A. So this could be a placebo, or this could be some existing treatment. And the other group is assigned a treatment B, which could be a new treatment. And then after the treatments have been assigned, we measure the outcomes. And let's say we denote the outcomes of treatment A by X1 through Xn, and the outcomes of treatment B by Y1 through Yn. So the question that we are interested in is there any difference between the two populations, X1 through Xn and Y1 through Yn? So does the treatment B have some other effect than treatment A? So we can state that a bit more formally within this framework of two-sample testing. So we say that let's say we have two sets of observations denoted by X1 through Xn, which are drawn IID from a distribution Px, and another set of observations, Y1 through Yn, drawn from a distribution Py. And we assume that these two data sets are independent, and we want to decide between one of two options. So the null hypothesis says that Px equals Py. Going back to a previous example, this would mean that the two treatments have exactly the same effect in a probabilistic sense. And the alternative says that Px is not equal to Py, so the two treatments have different effects. In this talk, I will make no further assumptions on the distributions Px and Py, and in particular, I will make no parametric assumptions like they belong to the exponential family or something like that. And our objective is to construct a powerful level alpha test psi. So psi is something that takes as inputs the data points, the 2n data points, and it maps to either 0 or 1. So 0 indicates that we accept the null hypothesis, that Px equals Py, and 1 indicates that we reject the null, and we believe that Px is not equal to Py. And we want to design a test psi that satisfies these two properties, that it controls the type 1 error at a given level alpha. So think of alpha as a small value like 0.05. So type 1 error is the probability of false alarms. So if the null is true, if Px is equal to Py, what is the probability that we end up deciding that Px is not equal to Py? That probability we want to control at alpha. And given that constraint, we want to maximize the power or the detection probability. So if indeed there's a difference between Px and Py, we want to maximize the probability that we are able to detect that difference. Okay, so any questions about the problem statement? Okay. So here are some characteristics which are more common in modern large-scale testing problems. So the first one, as I already mentioned, is that oftentimes we have to deal with data distributions that are quite complex, and they cannot be adequately represented by some parametric finite dimensional probability model. So we need to develop methods that can work in non-parametric scenarios. Another important property is that we often have to deal with really high volume of data, or equivalently, the sample size n is quite large. And to deal with that, we need to develop methods that are computationally efficient, or at least computationally feasible. One very interesting property is that we have to deal with data sets which are in different dimension regimes. So a lot of classical statistical theory has been done under the assumption that the dimension is fixed and the sample size is quite large. So the D is much less than N regime. But now we often see problems where D is comparable to N, or even D is significantly larger than N. So to address these scenarios, we need to develop methods which are dimension agnostic. That is, they are equally valid in all different dimension regimes. And finally, we also need methods that are applicable to sort of non-standard data types like images, videos, and graph valued data. So based on the previous slide, we can list the following requirements of any good test. So we want the test to be non-parametric, provably control the two types of errors, should be computationally efficient or at least feasible. That is, they should work for large N. They should be dimension agnostic, and they should work with general non-tabular data sets. Now, a popular class of tests that satisfy R1 and R5, so they are non-parametric and they can work on general spaces, are based on this notion of kernel maximum mean discrepancy, and I'll describe it in the next few slides. And there are several versions of this kernel-MMD based tests, and I've listed some of them. So all of these tests satisfy R1 and R5, but they also violate at least one of the other three requirements. And in this talk, I will describe a test that simultaneously satisfies all these five properties. Okay, so any questions so far?
So the original hypothesis test. So if I had a drug that suppose the mean effect was the same as placebo, but it just spread out the whatever the outcome was more, right? The P1, the PX would not be equal to PY, but that doesn't mean it's a better drug, right? The mean effect is the same, right? So it seems like I'm just curious what your thoughts are about that, because it seems like a very general alternative hypothesis.
Yeah. So that's why I said it was a simplified picture of clinical trials, because you want to use as much information as you have in setting your hypotheses in clinical trials. So I have thrown away all, I'm just saying is equal or not equal. But if you have other information, you should definitely use that. And if you can use parametric models, you should definitely use that. Yeah. Okay, so now I'll describe a class of tests based on this kernel maximum mean discrepancy metric. So let me begin by providing some information of how we define kernel MMD. So our goal is to essentially define a metric over the space of probability distributions. That is, for any 2 points P and Q, we want to assign a number which characterizes how close P and Q are. And one very useful way of doing this is by choosing a known metric space. So let's say we have some known nice metric space, script H, and if we can embed points from the probability space, the space on which we want to define a metric, into this new space, then we can use the distance between the representative points of P and Q as a proxy for the distance between P and Q. So yeah, so this idea shows up a lot in probability. But in order to implement this idea, we have two design choices to make. The first one is the choice of the embedding space, so the choice of script edge. And the second one is the embedding function, so the mapping from P to mu P. So at the very least, we would like this mapping to be what is called injective or one-to-one. So if it is one-to-one, then indeed the term rho will end up being a metric on the probability space. So because of several computational and analytical reasons, it turns out a good choice of the space script H is what is called a reproducing kernel Hilbert space. So a kernel K is a function which takes in two arguments from the observation domain, and it assigns a real number to it. So you can think of it as, in a very loose term, as a measure of similarity between 2 points. A good example to keep in mind is the Gaussian kernel. So it takes 2 points X and Y, and it assigns it that value. Now, the reproducing kernel Hilbert, so to every positive definite kernel, we can associate a reproducing kernel Hilbert space. And I won't explain it formally, but informally, the reproducing kernel Hilbert space consists of functions that can be reasonably well approximated by all finite linear combinations of this kind. So if you think of a Gaussian, you choose a bunch of points, x1 through, let's say, xm, and you fix one of the arguments. So you get a Gaussian centered at xi, and you take the linear combinations by some weights. All functions that can be well approximated by these kinds of combinations are contained in the RHS of the Gaussian kernel. So that's the first component. The second one is the mean embedding map. So it turns out a reasonably good map to take is the following. So to each P, we assign this term mu of P, which is the expectation of the K of X, which is centered at the random variable X. Now, once we have settled on these two components, we can then define the distance between P and Q as the norm of the difference between mu P and mu Q. And because it's an inner product space, we can write it as the square root of the inner product of mu P minus mu Q with itself. Okay, so just to go back to the picture, we have the original space. We are embedding it into the RKHS. So we have mu P and mu Q, which are the expectation of Kx under P and Q respectively. And then to get a distance between P and Q, we take the RKHS norm of mu P minus mu Q. And there exists an important class of kernels called characteristic kernels, for which this embedding, this map from P to mu P is 1-to-1 or injective, which in turn implies that MMD is indeed a metric over PX for these classes of kernels. Okay, so any questions about the definition? Okay. So I'll just one more slide. I want to say that there's an alternative interpretation of kernel MMD as a so-called integral probability metric. So this is a large family of distance metrics over probability spaces, and its definition is quite simple. So you choose any function class G and think of it as a bunch of test functions. And given any two distributions P and Q, you pass all test functions through this expectations. So take the difference, so absolute value of the difference of expectations of any test function G under P and under Q, and take the worst case value of this over all elements in the function class G. If the function class G is rich enough, then this distance will be able to detect differences between any two probability distributions, and it would indeed be a metric. So it's a simple exercise to prove that the MMD between P and Q is actually equal to the integral probability metric if we set the function class G to be the unit norm ball of the RKHS. Okay, so that gives us this alternative definition, which is you take all the test functions in the unit ball of the RKHS and take the difference in expectation. And I've removed the absolute value because if G belongs to the unit norm ball, so does minus G. So we don't need to carry here. Not F divergence, but yes. So total deviation is the only distance metric which is both an F divergence and IPM. So yeah, you can think it is. Yeah. So you took the Lipschitz functions and you get Botstein one. Yeah. Kolmogorov-Smirnov is also if you take all the indicators of minus infinity to X. Yeah, go on.
This is like an RKHS generalization. Should I think of this as like, because you want to measure things in terms of functions in the RKHS?
Yeah.
To define a metric that is valid for that map, for that embedding space.
Oh, so in some sense, this definition is independent of that one. It just turns out to be the same, but I want the function class to be rich enough so that these test functions can detect the difference between any two probability distributions. So for general spaces, it turns out you could do total variation, which is the indicator of all like measurable sets, which is very rich. So this is smaller in certain notions of capacity, but it still gives us a metric. So it's rich enough to define a metric, but it's also reasonably tractable and small enough in other notions of capacity.
Okay. So going back to one of the figures, you were trying to create a map. You were trying to create an injective map on the space. Yes.
Yeah.
So the distance between mu P and mu Q is the MMD that you described.
Yes.
And we haven't still discussed the map.
Oh, we did. So it is like, I don't want to go much into it because these are called function valued integrals. So, but yeah, they behave quite naturally for nice enough kernels. So yeah.
Can I ask a question about the same figure that you just had? I tend to think of embedding as maybe synonymous with lifting to a higher dimensional space, but
yeah,
1-to-1, so I shouldn't think of it that way, right? This is just
yeah, because that's yeah.
Think about dimension here, but
yeah,
I shouldn't think of it as dimensionality, lifting or reduction. It's kind of the
both
same.
are infinite dimensional spaces. So yeah. Yeah. So I guess the way to think of it is that there's some nice property on that space. We want to inherit it on our space. So we just find a representer point into that space. Yeah. Okay, so again, with some work, we can show that the supremum here is achieved by this function g star, which is mu p minus mu q normalized to have unit norm. And yeah, so it's proportional to mu p minus mu q, which gives us an alternative definition of MMD as a difference in means of this function g star. So the way to think of it is that for every p and q, there's a function g star in the unit norm ball, which provides us the maximum contrast in means of these two distributions p and q. And if we take the expectation of that, that gives us the MMD value. Okay. Okay, so now that we know how to define a distance between two probability distributions, we have a very simple path to define a hypothesis test, which is choose a positive definite kernel K. And then the second step is to construct a statistic, which is an approximation of the true MMD distance between Px and Py. So we don't know Px and Py, but we have observations drawn from Px and Py. So natural thing to do is to approximate that through the empirical distribution. And because MMD is a metric, it'll be equal to 0 if the null is true, if Px equals Py. So a natural thing to do is to reject the null if MMD takes a large value. So the key design choice here would be to choose the best threshold T alpha that sort of achieves the best trade-off between the type 1 and type 2 errors. Of course, yeah. The first step, okay, so in practice, it is a very important step to choose the best kernel for your problem, but I'll just assume for now that it is characteristic, and that's all I need for most of the talk. The next step is to construct the statistic, which we will use a very simple plug-in type of statistic. So recall the definition of MMD squared, which is the inner product between the embedding of Px minus the embedding of Py with itself. So a very natural idea is to replace the population embeddings with their empirical counterparts. So mu hat x is the embedding of the empirical distribution, or you can think of it in terms of replacing the expectation with an average. And similarly with mu hat y, just plug them into the inner product and you get a biased estimate of MMD squared. So debiasing it is very simple, but for our purposes, it does not affect much. So I won't go into the debiased version, but yeah, you can remove some terms from this expression and you get an unbiased version of MMD hat squared. Okay, so most of the existing methods use this kind of an estimate of MMD squared. And the final step is the choice of T alpha. So we want to define a test that rejects the null if the computed statistic exceeds some level T alpha. And just to remind you, T alpha should ensure these two things. So it should ensure that the type 1 error, so the probability of false alarm, is controlled at a given level alpha. So think of 0.05. And given that constraint, you want to achieve as high power as possible. So what is the ideal or the best choice of T alpha? Well, the optimal thing to do would be if we had, like if someone revealed to us the distribution of the statistic MMD hat squared under the null, then we should set T alpha to this value, T star alpha, which is the 1 minus alpha quantile of this distribution. So what that means is that T star alpha is the smallest value such that the probability assigned to the orange region is less than or equal to alpha. Okay. But as you can guess, we have no assumptions on Px and Py, so we don't know this distribution. So we have to approximate T alpha, T star alpha. And in the literature, there are two common ways of doing that. The first one is by using the asymptotic distribution. So what we hope is that there's some kind of universal result which says that for any Px and Py, as the sample size goes to infinity, the distribution converges to something tractable. And we can use the 1 mass alpha quantile of the limiting distribution, which will give us an asymptotically level alpha test. The second one is using permutation distribution, and I'll describe that in 2 slides. Okay, so just to go into a bit more details of the asymptotic approach. So as I mentioned, the statistic is MMD hat squared defined as follows. We cannot really directly find its distribution because we have no assumptions on Px and Py. So let's try the asymptotic null distribution. That is, let's take the sample size to infinity, but we immediately run into a problem, which is as follows. Because of the different dimensionality regimes, there are different limiting null distributions. So the classical setting, if you fix D and take the sample size to infinity, you get this called Gaussian chaos. So it's n times the statistic converges in distribution to an infinite combination of centered chi-squared random variables, where the weights lambda L are the eigenvalues of the operator associated with the positive definite kernel and the distribution. So again, it's quite intractable because these depend on the kernel and the distributions. and we don't really know the distribution. So, okay, it's quite intractable, but if you look at a different dimension regime, so if you take both d and n to infinity at a proportional rate, so let's say they converge to some number c, then you can show that the square root of n times MMD squared converges to a Gaussian distribution with some variance, which again depends on the distribution. So this leaves us with a problem because
Does that sigma squared depend on C as well?
yes. Now, this leads us to the problem because from a practitioner's perspective, we have just one n and one d. So which sequence should we assume this belongs to? There's no a priori way of assuming that. And yeah, so that's the problem. And so this is what I say, that the MMD tests are not dimension agnostic. Okay, so one alternative is to use permutation distribution. So here it uses the fact that if the null is true, then even if you shuffle the rows of the data set, the distribution remains the same. Okay, so here's the idea. You stack the data points together, and the blue rows are the x's and the red rows are the y's. And let's say you compute the statistic with this arrangement. So let's call that Tn. And now let's say we draw a bunch of random permutations and we recompute the statistic on each of them. So we randomly shuffle the rows. We label the first half of them as x's and the second half of them as y's. And with those x's and y's, we recompute the statistic. Let's say b times. Think of b as 500 or 1,000, depending on the problem. So you compute it these many times. But the key property is that if the null is true, then they are exchangeable. Okay, or in other words, the rank of the red statistic Tn among the b plus 1 values would be uniformly distributed. Okay, so based on that, we can set the rejection threshold as the 1 minus alpha quantile of the histogram of the blue statistics. Okay, so this is quite nice because this gives us an exact control of the type 1 error. And if we use more and more permutations, it will give us like higher and higher power and so on. So yeah, it performs quite well, but it leads to a b times increase in the computational cost. So that is the main drawback of this approach.
But B depend on n size of the data.
No, I think for any b you will get a control, but if the more number of permutations you get, the more finer your result would be. Yeah. Because the number of permutations just blows up, so you cannot hope to do all possible. Ideally, you should do all n factorial permutations, but it's not really possible. But yeah. Okay. So just to summarize, like we saw the two main methods, which is to use the asymptotic null distribution, where it has an intractable null in the low dimensional regime. It's also not dimension agnostic. We saw the permutation test, they perform quite well, but it requires us to recompute the statistic several hundred times, and it leads to an increase in computational cost. I want to mention that if you have access to a parallel computing infrastructure, then you should probably use permutation tests because yeah, it works quite well in those scenarios. There also are some other approaches. So there are concentration inequalities, which like have strong theoretical properties, but they're too conservative in practice. And there are some other ways of computing the statistic by subsampling, and they are known to have strictly suboptimal power. Yeah.
Like for reducing the computational cost of permutations, you could just do like a bootstrap, right?
So, well, they're conceptually different things. Like, so in permutation, we are not sampling without replace. So bootstrap, you usually do sampling with replacement.
Subsampling with the random block sampling.
So you're talking about permutation tests? Yeah, you can do that. Yeah. So that's what I said. I said you're doing B random subsample. Like, yeah. Okay. Okay. So yeah. So those were the problems with the existing methods. So in this section, I will describe a new method, which we call cross-MMD test. So the idea is we'll propose a very simple and new way of constructing an estimate. And this estimate will have a very simple standard normal limiting null distribution in all different regimes. And we'll see some interesting theoretical properties. But in practice, what this gives us is like a significant reduction in computation as compared to the permutation test. And we pay for that for a small loss in power. So that is the main takeaway from this section. Okay, so just to remind you, like, okay, so this is what we want to estimate. We want to construct an estimate for MMD squared, which is this inner product of mu x minus mu y with itself. So here's an idea. What we do is that given the data set, we split it into two equal parts, and we use them to construct two independent estimates of mu x and mu y, and we take their inner product. Okay, so just a bit more formally, so let's say we have this blackboard X and blackboard Y. We split them into two equal parts, X1 and X2, Y1 and Y2. You construct two independent estimates of mu X minus mu Y. So denote them by G hat 1 and G hat 2, and then take their inner product. So that is the first step of constructing the statistic. Just to hammer it home, here's a picture. So yeah, like we want to construct MMD squared. We had this gray data set. We split them equally into red and blue. Red gave us one estimate of mu X minus mu Y. The blue gave us another one, and we take their inner product. Okay, here's another way to look at it, which will be quite interesting and quite nice. So recall that we said that MMD was also an integral probability metric. So MMD between Px and Py is equal to the expectation of G star X minus G star Y, where G star was that one function which was proportional to mu X minus mu Y in the unit norm ball. So a way to think of our proposed statistic is that we split the data set. We use this, let's say one of them, let's say the second one, to construct an estimate of G star, or at least an unnormalized estimate of G star. And then we use the second split or the remaining split to approximate the expectation. Okay, so in some sense, we have reduced this problem to detecting the equality of two means of univariate random variables. So if you think of like, if you condition on the second half of the data, so assuming that G, okay, so yeah, just to repeat the steps, we split the data into two equal parts. Let's say we use the second half to construct an estimate G hat of mu X minus mu Y, and we use the first half to approximate the expectation. And if you condition on the second half of the data, so assume that G hat 2 is a fixed function, then it looks a lot like just the difference of means of two univariate random variables. Okay. And if you like, this problem of testing the equality of means of two univariate random variables has been studied for more than 100 years. And a classical approach is the so-called student's t-statistic. So the idea is you compute the difference in the means of two samples, and then you studentize it. That is, you divide it by the empirical standard deviation, let's call that sigma hat, times by square root of n divided by 2, just times by the sample size. Okay. That is what you should remember from this slide, but I'll also tell you a bit more details about what sigma hat is. So again, think of the statistic as a difference of two univariate means. So assume that if we condition on the second half, then it's like difference of u's and v's, where ui is g hat 2 computed at xi, and vi is g hat 2 evaluated at yi. So it's the difference of two means, and both of them are independent of each other. Hence, the empirical variance sigma hat of this term would be sigma hat x squared plus sigma hat y squared. The variances add up because they are independent of each other, and each sigma hat is just the empirical standard deviation of the u's and the v's. Okay, and the final statistic is obtained by normalizing with the empirical standard deviation and then times by the sample size. Okay.
I was expecting you to do the splits multiple times and then take the variance across those multiple splits. So that this is probably way more computation efficient than doing that.
Yeah. Okay. So here's how, so here's the plot of the empirical distributions of the statistic that we just proposed in the last slide for Gaussian kernel in two different dimension regimes. So I fixed D to, so N in both cases is 1000, sample size is 1000. In one of them, the dimension is equal to 20. So that approximates the low dimensional regime. And another one, the dimension is equal to 1000. So that is the high dimensional regime. As you can see, both of them look a lot like the standard normal distribution. So in all these different dimension regimes, our statistics seems to converge in distribution to normal 0, 1. And we can make that a bit more formal. So I won't state the formal theorem, but like the idea is that under very general conditions, we can show that the studentized cross MMD statistic converges in distribution to normal 0, 1. What that means is that if we construct a cross MMD test, which rejects the null, if the studentized cross MMD statistic exceeds the 1 minus alpha quantile of normal 0, 1. So that, so we can set T alpha to normal 0, 1, which is computationally as efficient as it gets because we don't have to compute anything. And this test is asymptotically level alpha. So I'll mention three levels of, or three variants of this result. So the simplest one is you fix a distribution, Px and Py, you fix a kernel, and you take the sample size to infinity. and assuming that the certain moment conditions are satisfied. So all these moment conditions will be satisfied for Gaussian because Gaussian is bounded. So all the moments are finite for any distribution. But assuming even this statement also allows for unbounded kernels, as long as these moment conditions are satisfied, we get a convergence in distribution to normal 0, 1.
It's not that little d, but the other little d, the problem dimension.
Yeah.
Is it fixed here?
So in this one, it's fixed because we are fixing the distribution. So the domain on
Oh,
which the
yeah,
distribution is satisfied. Yeah. So yeah. So that'll be the third version. Yeah. Yeah.
Like Google tests its statistics, it has only one as a plot and
Yes.
what's the medical thing?
What is that?
Magical thing.
Oh, I guess the way to think of it is like we are recreating students' t-statistic. So the behavior of students' t-statistic. So if you condition on the second half of the data, it looks like the difference of two univariate means. And so it's like, and once we studentize it, it looks exactly like a student's t-statistic, like a univariate random univariate observations and normalized with its standard deviation. So if you condition on the second half of the data, it looks like a t-statistic. So you would expect it to converge conditional on the second half to normal 0, 1, just as t-statistic does. But the difficult part is to move from the conditional statement to the unconditional statement, which does require a bit of work. Yeah.
Okay, and the reason why now D doesn't affect asymptotic the conditional.
Yeah, you can think of it as like we're projecting it in one dimension, like we are reducing the dimension. We're just taking the dimension out of the play by projecting it into this one-dimensional space. Yeah. That's an intuitive way of thinking. Okay, so that's the simplest version. A slightly more interesting version is where we again fix the dimension and the distributions, but we allow the kernel to change with sample size n. So imagine that we are changing the bandwidth of the Gaussian kernel with n, and it takes care of that scenario. And here's the more general version. So here we assume that we have a class of null distributions. So think of Pn superscript 0 as a sequence of distribution classes. If the kernel is Gaussian, then this Pn contains the entire, like all possible distributions. But they are changing with time. So the distribution classes are changing with n, or in other words, the domain over which they are defined could also be changing with n. And as long as they satisfy certain moment conditions, which are a bit complicated to write, but yeah, just as long as certain moment conditions are satisfied, we get a very strong uniform convergence result. So the red term is nothing but the Kolmogorov-Smirnov distance between the standard normal CDF and the CDF of the statistic at time with n observations. So the red term uniformly over all distributions in this distribution class Pn0 converges to 0. So yeah, so it's like very, very general scenarios and very robust convergence and distribution to normal 0, 1.
What's the null process here? Is all the px equal to py for
Yes.
all n?
Yes. Yes. Okay. So yeah, under very general scenarios, we get a standard normal limiting distribution. And just to illustrate that, here we have n equals 200. So I want to simulate the scenario where dimension is even larger than the sample size. And even for some small sample sizes like 200, we see reasonably good convergence to normal 0, 1 for different kernels like Gaussian and quadratic. Okay, so that was all about the performance under the null. Now we want to see how this test performs when the null is not true. So the bare minimum requirement of any test, if the null is not true, is that if you keep the problem fixed, if you keep increasing the sample size, you want it to be able to detect it eventually. So which is what is formalized in this statement. So if the kernel is characteristic and if some second moment conditions are satisfied, then the cross-MMD test is consistent. That is, as the sample size goes to infinity, the probability that it exceeds the threshold Z1 mass alpha is equal to 1. So that's, okay, a good sanity check. But a more interesting result is you want to understand its performance against local alternatives. So I will describe what local alternatives are. So at a very high level in words, we'll do these two things. So we'll first restrict our attention to some smaller class of alternatives. And then we want to find out for every sample size n, what is the closest alternative in this family of possible alternatives that can be detectable by our test psi. Just as an example, let's consider the case where we are working with real valued observations and the class of alternatives that we are looking at look like this. So it consists of pairs of distributions, P0 and P delta. P0 is normal 0, 1, and P delta is normal delta 1. Okay, so just a mean shift detection. And so this is the class of alternatives. So what we want to understand in this setting would be delta star n. So the behavior of delta star n with n. So for any sample size n, what is the smallest alternative which our test can detect with, let's say, some sufficiently large power? So how does this behave? Here's just some empirical results on the same problem. So I plotted the delta star n as sample size n increases. And what it says is that, okay, so this denotes the detection boundary. So this is the boundary below which things you cannot really detect with high enough power and above which you can detect with sufficiently large power. And we want to understand how this boundary behaves with the sample size n, probably for a larger class than the Gaussians, but so that is the main result. I will first explain the result in words, and then I will introduce the more formal statement, which has got lots of notations. So the idea is that we'll fix the domain to R to the D, and we want to look at these distributions which admit densities, and these densities are smooth. The smoothness of these densities will be parameterized by some parameter beta. So think of this beta as characterizing the number of derivatives the densities have, okay? So we look at these kinds of delta separated alternatives. So the alternatives will be all pairs of P's and Q's. So such that the densities of P and Q are separated in L2 norm by this level delta. Okay. And again, our goal is to understand what is the smallest delta n that can be well detected by our cross MMD test. And what our result says is that delta n behaves in this way. So is n to the -2 beta divided by d plus 4 beta. Yeah, so the detection boundary becomes closer if the function is more smooth. So if beta increases, it becomes closer, and it becomes farther away if the dimension increases. Okay.
Theoretical or no, not a theoretical?
No, this is theoretical.
Theoretical.
Yeah. And can any test do better than this? Not at least in terms of rate. So no test can achieve a better rate. So the detection boundary decaying at a better rate, but there do exist tests that probably achieve better constants than us because we are doing sample splitting. Okay, so slightly more formally, the smoothness we will assume is what are called Sobolev balls. So yeah, Sobolev functions for any beta are functions which have these many weak derivatives. And yeah, so yeah, I won't describe that formally, but we assume that we are working on this d-dimensional Euclidean space where the distributions admit densities. The null class is all p times p, where the density lies in the Sobolev ball. And the alternative class are the so-called delta n separated alternatives, where the densities lie in this smooth class of functions, and they are separated in L2 by at least delta n. And the result says just what I mentioned in the previous slide, that if you assume that delta n is greater than or equal to a constant times this rate, and if we run the cross MMD test with a Gaussian kernel whose bandwidth increases or whose scale parameter increases at a certain rate depending on the smoothness and the dimension, then we have these two properties. So the test will control the type 1 error uniformly at the level alpha as the sample size goes to infinity, and it will also achieve asymptotically, it will achieve power 1, again, uniformly over the sequence of delta n separated alternatives. And Lee and Yuan proved that if you look at detection boundaries that are strictly smaller than this rate, then no level alpha test can achieve asymptotic power 1. So in that sense, we cannot really hope to achieve a better rate of the detection boundary with any test, but there do exist tests that probably have better constants than us because we do sample splitting. So we are at least losing half of the power. Okay. And just to go back and verify our intuition, so the example that we took was for Gaussian distributions, which are infinitely differentiable. So for them, the smoothness parameter is beta. If you plug that in, the rate becomes equal to 1 over square root of n. And here's what I have. So the blue line is the empirically observed detection boundary, and the dashed line is the best 1 over square root of n fit. And it does seem to fit quite well. So some verification of the theoretical results. And just to compare the performance of our proposed cross MMD test with the MMD permutation test. So the left plot shows the power versus sample size. For the same value of sample size, as you can see, the MMD permutation achieves a better power than our proposed test. But on the right side, we have replaced the x-axis from sample size to the running time. And in this case, the order is flipped. So to achieve the same power, let's say 0.8, MMD requires 2 orders of magnitude more compute than cross MMD. So the main takeaway is that if your bottleneck is the running time, not the sample size, then it makes sense to use cross MMD. Otherwise, you should use the MMD permutation test. Okay, so just to summarize everything so far, we saw that we proposed a new statistic that we call the cross MMD statistic. We saw that it has a standard normal limiting distribution in all different dimension regimes. We saw that it's consistent against fixed alternatives. It has minimax rate optimal detection boundaries against local smooth alternatives. And in practice, it gives us 2 orders of magnitude reduction in computation at the price of a small loss in power. So any questions about the previous section? Yeah, I mean, there exists a lower bound of this kind, which says like Lee and Yuan. Yeah.
So you split the data equally here.
Yes.
Is that the best thing?
Yes.
Yeah,
Yeah.
okay.
So if you, so we analyze it in the general setting, but you can also analyze it in a slightly more restricted setting. Let's say detecting means of Gaussians or something.
Okay.
In that case, you can get an explicit expression for the power, which has that term, which is like C, let's say, that ratio of splitting,
I see.
and that is maximized for.
Okay.
Yeah.
Nice.
Does this have any connection to the double estimator?
The Cherny-Zhukov one.
Like when you estimate the max of a sequence of random variable, you split the data set into 2, first identify which one likely to be the largest one, and use the other data set to estimate the mean. So separate the division.
I think it could be. I think it could be, but I'll have to think a bit more. Yeah, it could be. Yeah. Okay, so I'll just quickly talk about a related problem of independence testing and how we can apply the same ideas to this problem. So here's the definition. Here we have n paired observations. So x1, y1, x2, y2 through xn, yn. These are drawn IID from a joint distribution pxy. And we want to test whether pxy is equal to the product of its marginals. That is our x and y independent or not? And again, we make no further assumptions, and we want to construct a level alpha test of independence. So one natural idea is to use a metric, so-called Hilbert-Schmidt independence criteria. And what you do is that the HSIC of pxy is equal to the MMD squared of pxy and the product of its marginals. So that seems a natural thing to do, but there's a bit of a complication because we do not have observations from the red distribution. So unlike the 2-sample testing where we had observations from X and Y, here we do not have that. So that is the main source of like the technical difficulties in extending this idea to this case. But nevertheless, we can still repeat almost all the same arguments. So now we choose 2 kernels, one on X, like script X, and one on Y. So L on the space Y. And we define these 3 embeddings. So the embedding of the joint distribution, which is denoted by omega, embedding of, let's say, px, which is denoted by mu, and the embedding of py, which we denote by nu. And just the definition of HSIC is just MMD squared. So we take their inner product to get the definition of HSIC. And again, all the same results, like for characteristic kernels, this embeddings would be 1-to-1, and hence this HSIC is equal to 0 if and only if X and Y are independent of each other. And they also inherit the same problems. So HSIC also has different limiting distributions in different dimension regimes. And if you use the permutation test, you have to increase the computation cost. So to address that, we will follow the same ideas. So you split your data set into 2 equal parts. You construct these 2 independent estimates of the embeddings, so g hat 1 and g hat 2. And you take the inner product to get the cross HSIC. And finally, we define the studentized version after constructing an empirical estimate of the standard deviation, sigma hat n. And using this statistic, we reject the null if it exceeds the 1 minus alpha quantile of the standard normal. So Z1 minus alpha is the 1 minus alpha quantile of the standard normal distribution. So almost an exact repetition of the steps that we used for cross MMD. But I guess the main difference, like the technical difference, is that when we were looking at MMD, we had it as a difference of two independent means. Here, the independence goes away. So if you condition on the second half of data, you have the difference of these two things, but they're not independent. And that is the main source of technical challenge. But in the end, we can prove almost the exact same set of results. So under very general conditions, you get the convergence to normal 0, 1. And just to verify that, here's like two different kernels and two different dimension regimes in both of them. Even for n equals 1000, the convergence to normal is quite nice. Again, for any fixed alternative, we get consistency as long as K and L are characteristic, and we get rate optimal detection boundaries against appropriately defined smooth alternatives. And here's a comparison with HSIC permutation and the cross HSIC test, and we see the same pattern. So if you plot power versus sample size, the permutation test is better, but if you plot power versus running time, the order is flipped. So the conclusion is the same, that if your bottleneck is running time and not so much the observations, you should use cross HSIC. Otherwise, you should use the permutation test. Okay. Yeah, so I think I've already 45 minutes. So I'll quickly talk about some of my current work and some interesting directions for future work. So one of the things that I did not talk about was the problem of kernel selection. So I just said I want the kernel to be characteristic, but in practice, the performance of the test does depend a lot on for example, the scale parameter. So I will talk a bit about how we can choose the scale parameter in the next couple of slides. But I just want to mention two other directions that are interesting to think about. The first one is like if we can prove something beyond just assuming IID observations. So under maybe some kind of mixing conditions or some other kind of dependent random variables, if we can hope to prove asymptotic normality. And the third one is to go back to the IPM-like definition of kernel-MMD. So there also exist other distance metrics like Wasserstein or F divergence, which have a variational definition. So can we hope to repeat the same program for those other distance metrics and get some kind of nice asymptotic distributional result? Oh. So yeah, I'll just end very quickly by talking about the problem of bandwidth selection. So as I mentioned, most kernels have some free hyperparameters. For example, the Gaussian kernel has this scale parameter or the bandwidth parameter. And in practice, the performance of the test will strongly depend on this scale parameter. So here's one way we could think of addressing that. So let's say we choose B min and B max, so a range in which we want to fix the band, or we want the bandwidth to lie. Then we can define a statistic as the supremum over all choices of the kernel in this kernel class and compute the statistic for each of those kernels. So the statistic could either be MMD or cross MMD, and we could look at the maximum value over all these bandwidth value, over this range of bandwidth. So it's natural to expect that the test that we construct using this statistic would be much more powerful, but then it's difficult to calibrate, difficult to choose the rejection threshold. So here's how one way we could proceed is to treat this as a stochastic process. So we have a collection of statistics indexed by the family of kernels, and let's assume that there's some weak convergence, so some distributional convergence of this stochastic process to some nice limiting stochastic process, let's say G. Then we could look at the supremum of the limiting stochastic process to calibrate the test. And again, we could set Z star 1 mass alpha as the 1 mass alpha quantile of G star, and that would give us a asymptotically level alpha test. But the problem is that we get a new notion of lack of dimension agnosticity, in this case for the MMD process. So let's say we wanted to do that program for MMD tests. So there exists a result by Nolan and Pollard, which said that if you fix a class of kernels and you take the sample size to infinity, plus a bunch of other conditions on the capacity of the kernel, then you get a convergence, like a weak convergence to what is called like a Gaussian chaos process. So it's a Gaussian process, like an infinite linear combination of Gaussian processes. Okay. And we also have some preliminary results, which if you slightly modify their result and look at a sufficiently increasing class of kernels under certain like technical conditions, we can show that MMD process converges to a Gaussian process. And then we are again back to the same problem, but at a much wider scale, which is given one sample size and class of kernels, which limiting process should we use to calibrate the test? And what we hope to prove is something like this, which if we can construct a cross-MMD process whose functional convergence is independent of the specific type of sequence of function classes that we use. So I haven't figured out all the details, but that's what I'm currently working on. Okay, so I'll just end with a quick summary. So we saw some kernel-based methods which are quite useful for non-parametric testing problems like two-sample testing, independence testing. And we saw that the existing methods are either not dimension agnostic or they are computationally expensive. And then to address that, we proposed these cross-MMD and cross-HSIC tests that have nice limiting distributions in all different dimension regimes. They do not require permutations and they have some nice theoretical properties. And we also saw that there are several other interesting directions to pursue for future work. So with that, I will stop my presentation. Thanks.
Thank you very much. Any questions?
There's a chat.
Yes, it's all good.
So the last part where you're trying to find the best bandwidth, if you did the max over K, which is like max over B here, does that work with the permutation test? Can you
I
just
don't know.
divide
I
these
think
others?
so. Yeah, but I have to think a
It's
bit
super
more.
expensive.
Yeah,
and now
yeah,
you've got
yeah,
like two loops
yeah,
or whatever, but
yeah,
okay, I just
yeah,
wondered if conceptually
yeah,
it would work.
yeah.
And then do you think there exists a sort of best of both worlds where you can get rid of maybe that square root of 2 of statistical power loss and reduce computation, or do you think there's a fundamental trade-off?
I'm not sure actually. Yeah,
Yeah.
I'm not sure. Yeah.
And then my last question is, throughout you assumed the number of X samples is the same as number of Y samples, and I'm guessing that might just be for reasons.
Yeah,
of
yeah,
practice,
yeah.
not really needed.
Yeah, they could be different. Yeah, yeah.
Okay.
But we do need some restrictions. So like the limiting values shouldn't be like log n versus
Yeah,
n or something
right,
like that.
you need
Yeah,
to
yeah,
cover
yeah,
ratio.
yeah. The ratio should be strictly bounded away from 0 and infinity.
Yeah, okay.
I think Vijay has a question.
Yeah, thanks, Shubhanshu. It was a great
Oh,
talk.
What do I
Can
do?
you hear me? Yeah. Can you hear me? Hello?
Crazy sense, man.
Yeah, Vijay.
Right up to go unmute.
Oh, I see. Can you say that again?
No, can you hear me?
Yeah, now.
Yeah, we can.
Yeah, okay, great. Yeah. Oh, thanks for the excellent talk. So I had a slightly different question. So the two sample test that you were saying, essentially, seems like the most strongest application is this independence testing, right? Maybe there are other applications too, but
Yeah.
I would think that a better sort of a more general problem would be X and Y, the distributions are close,
Okay.
or they are far apart.
Oh, yeah, yeah.
And I suppose this method won't, but
Yeah, like suitably modified versions of these methods should work for that kind of problem. So yeah, I think there has been a lot of work recently on that. They're called like closeness testing in the TCS literature, and
Yeah.
they look at discrete distributions, and they have like a lot of theoretical results on that. So yeah, I think that problem is also quite well understood, and not exactly the same, but similar ideas could be used there as well.
and do they have the same sort? I mean, I assume they would have the same dimension issues and.
Oh, so most of the works I've seen are on like multinomial testing. So they work the discrete distributions.
No, thanks.
Yeah.
You mentioned bias like way back slide
Yeah.
14. Is the bias known to be positive or negative, or it could be anything? Because it would affect, your comparison to the threshold if you know it's
Yeah,
positive
yeah.
bias.
So, oh, that's a good question. I think it should be by Jensen's inequality, whichever direction that tells us, because what we're doing is like, essentially we're trying to estimate x squared by estimating x and plugging it in. So
Okay.
yeah, I cannot remember which direction it says, but yeah, yeah, yeah. So it's inner product square, which we are approximating by, yeah.
Any other question? Okay. If not, let's thank.
Should I end the meeting?
Yes.
Stop.